Hello friends, I welcome you in lecture number 2 on exponential distribution. In this lecture we are going to discuss what is mean and variance of exponential distribution. So first we recall the definition of mean and variance. We know that if x is a continuous random variable, then expected value of x is given by this formula, integral from minus infinity to infinity x times fx dx, where fx is nothing but pdf of random variable x. And if we want to find out variance of x, we have this formula. We find out expected value of x square and we take square of expected value of x, and this is denoted by mu. Mean is denoted by mu and variance is denoted by sigma square. So this we can write as expected value of x square minus mu square also. And one more thing, suppose x is a random variable and g is some function of random variable x, then expected value of this function g is nothing but integral from minus infinity to infinity gx times fx dx. So this is required for expected value of this x square. So if we have gx equal to x square, we will put this expected value of x square equal to minus infinity to infinity integral of x square into fx dx. So with this in mind, we try to find out mean and variance of exponential random variable. Okay, before that we first write down the probability density function of exponential random variable. So as we have discussed in lecture number 1, PDF of exponential random variable is fx equal to lambda times e raised to minus lambda x if x is non-negative, and it is 0 if x is negative. So now we try to find out mean and variance of exponential random variable. So for mean, we start by definition. By definition, mean of exponential random variable x is mu equal to expected value of x. This is by definition minus infinity to infinity integral of x times density function with respect to x. Now this we can write as a sum of two integrals, integral from minus infinity to 0 and integral from 0 to infinity, because our density function is different for non-negative and negative values. Now if we consider this integral, then here x is negative, here limits of x are minus infinity to 0, so x is negative, and if x is negative, value of fx is 0. So here we have integral of 0, which is 0, and in this part fx has value lambda into e raised to minus lambda x. Here limits of x are from 0 to infinity, that is x is positive, and if x is positive, value of density function is lambda times e raised to minus lambda x. So here we have integral from 0 to infinity x times lambda e raised to minus lambda x dx. Now this is improper integral. So we know that if we have improper integral with upper limit as infinity, we write it as a limit of proper integral. We replace this infinity by a and we consider limit as a tending to infinity, and x times lambda e raised to minus lambda x dx. So first we will find out this integral, and then whatever we obtain here, we will take limit of that function as a tends to infinity. Now to find out this integral, we recall the formula for integration by parts. Suppose we have two functions of x in the product, then we have this formula u as it is integral of v, which is denoted by v1, minus derivative of u times integral of v1, which is denoted by v2, plus derivative of u dash, that is second derivative of u, times integral of v2, which is denoted by v3, and so on. And here in this product we will consider that function as u whose derivative is 0 after some finite number of steps. So here we consider this x as u because second derivative of x will be 0, and we consider this lambda times e raised to minus lambda x as v, and we apply integration by parts. So this is equal to limit a tending to infinity. First we consider u as it is. Here u is x, integral of lambda e raised to minus lambda x. So this is going to be lambda as it is. Integral of e raised to minus lambda x is e raised to minus lambda x divided by minus lambda, that is minus e raised to minus lambda x. Here lambda is positive, so we can cancel out. So here we directly write minus e raised to minus lambda x minus derivative of u. Here u is x and derivative of x is 1 into integral of this v1. So integral of e raised to minus lambda x is e raised to minus lambda x divided by minus lambda, and we already have positive sign, so we have negative negative positive, and limits are from 0 to a. So this is by integration by parts. Now we simplify this. This we can rewrite as limit a tending to infinity. First we write in another form. We can rewrite e raised to minus lambda x as 1 over e raised to lambda x. Same thing here, 1 over lambda times e raised to lambda x. Limits are from x equal to 0 to x equal to a. So now we put the values of x. First we put upper limit. Upper limit is x equal to a, so we write minus a divided by e raised to lambda a. Here we substitute x equal to a, and same thing here we put x equal to a. So we have 1 over lambda times e raised to lambda into a. This is for upper limit, minus x equal to 0. So here x is in the product, so we have 0 divided by e raised to 0, which is 1. So 0 by 1 is 0, and minus here we have lambda, and if we take x equal to 0 here, e raised to 0, which is 1. So we are left with 1 over lambda. So this we can rewrite as we can take limits here. So this limit of negative of this, which is limit of negative of limit of e over e raised to lambda a as a tending to infinity, minus limit a tending to infinity 1 divided by lambda times e raised to lambda a. Here negative negative positive, and limit of 1 over lambda as a tending to infinity. Now if we observe here, if we take a tending to infinity here, then we have infinity by e raised to lambda into infinity. Now lambda is positive, so lambda into infinity is also infinity. So we have infinity by infinity indeterminate form, and we know that if we have infinity by infinity form, we can apply L'Hospital rule, and here variable of limit is a, so we differentiate numerator and denominator separately with respect to a. So derivative of a with respect to a is 1. Derivative of e raised to lambda a with respect to a is e raised to lambda a times lambda. Coefficient of a is lambda. Let me write properly. Here we have derivative of e raised to lambda a is e raised to lambda a into coefficient of a which is lambda, minus here 1 over lambda into e raised to lambda into infinity. If we take a tending to infinity, we have lambda into infinity, which is infinity because lambda is positive. And here 1 over lambda is independent of a, so it is constant. So limit of constant is constant itself, that is 1 by lambda. And here in first limit we have applied L'Hospital rule. Now if we take limit as a tending to infinity, here we have 1 over lambda into e raised to infinity. E raised to infinity is infinity, so we have minus 1 over infinity, that is going to be 0 plus 1 over lambda. And same thing here, e raised to infinity is infinity, lambda is positive, so here we have 1 over infinity, this we can put 0 plus 1 over lambda, and again 1 over infinity is 0, so finally we have 1 over lambda. So therefore mean of exponential random variable is 1 divided by lambda, where lambda is parameter of exponential distribution, which is always positive. Now we try to find out variance of x, and we know that variance of x can be computed using this formula also, expected value of x square minus expected value of x whole square, that is expected value of x square, and this is mu square. So we have find out value of mu. So for this we first find out expected value of x square. So this is equal to minus infinity to infinity x square times probability density function of random variable x. So here also we write this integral as a sum of two integrals, minus infinity to 0 x square fx dx plus 0 to infinity x square fx dx. So this is going to be 0 because fx is 0 if x is negative, and here we consider fx equal to lambda times e raised to minus lambda x dx. So again we have to apply integration by parts. Derivative of x square is 0 after some steps, so we consider u equal to x square and v equal to lambda e raised to minus lambda x, and we apply integration by parts. So x square as it is, integral of lambda e raised to minus lambda x is minus e raised to minus lambda x minus derivative of x square, which is 2x, integral of minus e raised to minus lambda x, that is going to be e raised to minus lambda x divided by minus lambda into negative, so we have lambda here, and plus derivative of 2x, which is 2, and here e raised to minus lambda x has integral e raised to minus lambda x divided by minus lambda, so here we will have square of lambda, and limits are from 0 to a. Okay, here I have to write this integral as, okay, here I forget to write this as a limit of integral from 0 to a x square times lambda e raised to minus lambda x dx, and a tending to infinity. So here also we have limit as a tending to infinity, and once we put limits we have, okay, we will put limits in the next step. So this is limit of this bracket, and limits are from 0 to a. So first we simplify all these things, and then we will substitute limits. This is limit a tending to infinity of, here this we can rewrite as x square over e raised to lambda x minus 2x e raised to minus lambda x can be written as 2x over lambda times e raised to lambda x, here we have negative sign, minus 2 e raised to minus lambda x is 1 over e raised to lambda x. Limits of x are from 0 to a. So this I have rewritten here, minus 2x, this is in the denominator, and now we can put limits of x. First we put x equal to a and then minus x equal to 0. So limit as a tending to infinity. If we put x equal to a, we have minus a square over e raised to lambda a minus x equal to a, so 2a over e raised to lambda a minus 2 over lambda square e raised to lambda a. This is for x equal to a. We have replaced x equal to a everywhere in this expression. Minus, if we put x equal to 0, these first two terms will be 0 because we have x here. Here we have x square and here x, and denominator becomes non-negative. It becomes non-zero for x equal to 0. So this is minus 0 over e raised to 0, that is 1. So 0 by 1 is 0. Same thing here, 2 into 0 over lambda into e raised to 0, which is 1. So this is also 0 because lambda is positive, and this is minus 2 over lambda square into e raised to 0. E raised to 0 is 1. So for x equal to 0, we have contribution from this term only, minus 2 over lambda square. Now we can write this as, this is going to be minus limit a tending to infinity a square over e raised to lambda a minus, we can take constant outside, 2 over lambda is independent of a, and we have limit a tending to infinity a over e raised to lambda a, and minus 2 over lambda square, limit a tending to infinity 1 over e raised to lambda a. Okay, this 2 over lambda square is independent of a, so that I have taken outside. Same thing here, 2 over lambda is outside, and we have negative sign. This is going to be 2 over lambda square into limit of 1, that is 1. So this is independent of a, so its limit as a tending to infinity is 2 over lambda square. Now if we consider a tending to infinity here and here also, we have infinity by infinity forms. So we apply L'Hospital rule here. So this is going to be minus limit a tending to infinity, derivative of a square is 2a, and derivative of e raised to lambda a with respect to a is lambda e raised to lambda a. Same thing here, here also we have infinity by infinity form. So we take derivatives separately. Derivative of a is 1, derivative of e raised to lambda a is lambda e raised to lambda a, and if we take limit as a tending to infinity, here we have 1 over e raised to lambda into infinity, that is 1 over e raised to infinity, because lambda is positive, this is 1 over infinity, which is 0. So I can directly write limit of this as 0. So I have minus 0 and plus 2 over lambda square. Now same thing here, limit of this is also 0 because we have 1 over lambda into e raised to lambda a. If I take a tending to infinity, I have 1 over lambda into e raised to infinity, and lambda is positive, so I have 1 over infinity, which is 0. And here again we have infinity by infinity form. 2 into infinity is infinity divided by lambda into e raised to infinity, that is also infinity. So we again take derivative of 2a, which is 2, and derivative of lambda e raised to lambda a is lambda square e raised to lambda a, this is 0, and minus 0 plus 2 over lambda square. So this is equal to, now if we take limit as a tending to infinity, here we will have 2 over lambda square into 1 over e raised to infinity, and this is 0, so we have 0 here. And finally we have expected value of x square equal to 2 over lambda square. So therefore expected value of x square is 2 divided by lambda square. And now we have variance of x equal to expected value of x square minus mu square. Expected value of x square is 2 over lambda square, and value of mu is 1 by lambda, so that is equal to 2 divided by lambda square minus 1 divided by lambda square, which is nothing but 1 over lambda square. So therefore variance is 1 over lambda square and mean is 1 over lambda. And we can write as a note that if we are interested in the standard deviation, then standard deviation is nothing but square root of variance. So square root of 1 over lambda square, which is 1 over lambda, and this is nothing but mean of exponential random variable. So for exponential random variable, mean and standard deviation are equal, they are having same value, which is 1 over lambda, and variance is nothing but square of mean or square of standard deviation, in particular for exponential random variable. So in this way we can find out mean and variance of exponential random variable. We just have to remember these two formulas, that is mu is given by integral of x times fx from minus infinity to infinity, and we have this shortcut formula for the variance, that is expected value of x square minus mu square. So in this lecture we have discussed what is mean and variance of exponential random variable. Sometimes they ask you to find out mean and variance of particular random variable, so you must be able to find out using formula. And here if you observe, we have repeated application of L'Hospital rule. Okay, here we are applying L'Hospital rule 2 times for this function, for this limit. We applied L'Hospital rule 2 times. So if you don't want to write down all these things, you can simply apply this formula directly. We have this formula that if we have x raised to n divided by e raised to x as x tending to infinity, then this is always 0 for positive power of n, or for positive for natural number. Here we require natural numbers only. So if we consider any positive integer n and we have x raised to n over e raised to x, then we can directly write 0, because exponential function grows faster as compared to polynomial function. So if we want to find out this limit, we had this type of limit here, a square divided by e raised to lambda a square divided by e raised to lambda a. So because lambda is positive, I can directly write this limit equal to 0. Okay, so that is valid if you don't want to apply L'Hospital rule repeatedly, and if you want to minimize your calculations, you can use that formula directly. You can directly write this limit equal to 0. So this is all about today's session. I hope you like it. Thank you.